Hello and welcome to this podcast for Electropages. I'm your host, Robin Mitchell. Today we have a very special guest all the way from TI, Texas Instruments. It's none other than Mark Ng, and that is the correct way to pronounce it after doing the intro again because I get it wrong. And so without further ado, please introduce yourself, who you are, what you do, and what you do in your free time.
Hey, Robin. I'm actually very impressed because I think that's the first time a Westerner, even myself, having grown up in the US, has actually pronounced my last name correctly. As I mentioned, I don't even think I know how to pronounce that correctly. So thank you for that. I am the general manager inside of Texas Instruments for what we call HEV-ED, as well as body electronics. So that's essentially what we call electrification in industry. So that's like onboard chargers or battery management systems or traction inverters. And also on the body side, we have things like automotive body motors or zone control modules or, general, thermal management types of applications. So that's basically, aside from ADAS and infotainment types of systems, I'm basically responsible for working with customers, both OEMs as well as tier ones worldwide on next generation platforms. So I have the pleasure of basically looking at what's new from, let's say, model year 25 and beyond, because we're literally working on next generation architectures.
Sounds like you've got your hands full there on quite a number of different areas of the automotive industry. But before we dive into the products themselves, I want to actually start by looking at the main sort of theme of this podcast, and it really comes down to vehicle safety. And I would ask you, what's the biggest challenge that you see in vehicle safety these days, especially when it comes to the electronic side of things?
Important topic. I think, as I mentioned, all these OEMs, they're all working on next generation platforms, and the architectures are dramatically changing. One of the most important aspects is the autonomous driving, right? And in order to work toward this type of autonomous vehicle, you need to have devices that are functionally safe and the overall system that is architected to be functionally safe. And so what's difficult there is, you need to have to define a system to be redundant, to have the plausibility checks, the diagnostic checks. You also need to have all of the silicon be able to work together, as well as not only hardware, but also the software. So I would say that the challenge for this kind of safety is kind of developing this overall ecosystem to meet the OEM's functional safety goals, right? So functional safety is really a complex topic. There's something called ISO 26262. There's different ASIL levels that are associated with things. But as we look at safety, it's a very broad topic that encompasses everything from what we'll talk about today is like, the radar devices or contactors or, pyrofuse control. Those all require different types of functional safety levels, so-called ASIL D or ASIL C or ASIL B and so on. So really, it's the ecosystem of devices to make them hardware and software, be able to meet the requirements of the overall metrics of the system. Now,
one thing I've seen myself in the automotive industry is that obviously as new technology gets introduced, it slowly finds its way into vehicles. And I always find that vehicle technology tends to be maybe a few years behind, standard off-the-shelf commercial technologies, and that's because, like you say, the stuff you get from the shop doesn't need to be as safe as what you find in a car, as you say. But what I find is that in the sort of the past 5 to 10 years, there seems to be this sudden acceleration in capability and what vehicles can do. And my primary concern is that rapid integration of technology might be too fast, such that, like you say, do we know that it's going to be safe in term, functionally, is it going to be safe because it's been integrated so quickly?
I actually read an article on the paper yesterday. I think it was in one of the main, Wall Street type of journals, and it actually addressed this point. And the traditional OEMs that we've all been used to for internal combustion engine, right? The European and the American vendors, right? These are, and even the Japanese, these are very tried and true designs. And I think what really shook up the industry was, the explosion of electric vehicles and kind of China coming into the overall picture and saying, we want to do our next platform not within, let's say, 5 years, because it would literally take 5 years to do this type of design from scratch, from beginning to end. But if you look at these Chinese design cycles, and this report was talking about it, they're literally, from beginning to end, they're looking at, less than 48 months, right? And they're literally pumping out vehicles every single year, because people are interested
48,
in.
Sorry, 48 months from start to completed design.
Mm-hmm. And so that's, to your point, it is scary, right? Because it's, how do you do that? And the article talks about, we can do a lot of virtualization, right? So whereas a lot of tests had to be performed in actual hardware tests, I mean, now we can do them via virtualized systems or hardware and loop simulators and so on. So I think they've moved to a lot of this type of, software type testing, but it's still very valid. Your point is that, are these vehicles safe? And, I guess the cynical answer is, only time will tell.
Only time will tell.
Right. But I think I think my answer is, with the devices that we are working with these vendors on, again, we talked about safety from the very beginning. These chips that are enabling this next generation of electrified vehicles are specifically designed for higher levels of autonomy. They are also designed specifically for functional safety types of applications, right? So, we have devices that are designed to work specifically in that type of mechanism, or in that type of vehicle. Whereas in the past, before we had this explosion of battery electric vehicles and all, we didn't really have chips that were optimized for vehicular types of architectures. So that's kind of one thing that mitigates, right? Yes, the cycles are shorter. The OEMs are, pushing the limit in terms of design cycles, at least the Chinese ones are. But we are actually supplying them, and they are working with state-of-the-art silicon, which actually has significantly advanced and tailored features for safety.
And that's, I think, a really interesting point you said there. So before this explosion of like dedicated silicon for EVs, it was kind of like people were trying to make EVs by slapping it on top of a traditionally internal combustion engine vehicle, and casing how all that works and fits together. So you kind of had that like almost like haphazard design of trying to mix the two together. But now what you're saying is that because we've got hardware that's absolutely dedicated just for EVs, it's a lot easier to develop and deploy.
Yes, and if you look at the biggest, battery electric, maker in the world, right? Their advantage was that they started from battery electric, right? And so the other manufacturers started from internal combustion engine, and they're basically trying to catch up to say, okay, we need to move toward hybrid, and then they move toward battery electric. And so there is a huge shift in industry right now, and I would say it's actually kind of like let's say a world fight in terms of who's gonna race to create the right platform to be able to continue to crank out new designs and meet new architectures and so on. And so it's a race between the internal combustion engine kings versus kind of like the newbies on the market, or not so much newbies, but there's a lot of new people on the market, right?
But even and this comes back to that original point, which is that even if you're a king in the field of internal combustion engines, that does not mean you're going to win the EV race, simply because it's so out of your area. The only thing I suppose they've got going for them is that they know how to put four wheels onto a case. But in terms of like the electronic side, the software side, it's a completely different story. You're talking about new technologies like, I don't know, silicon carbide, possibly GaN, all those different things coming together. And so those automotive makers have to sit there and go, how do we basically fundamentally change everything that we've done for the past 100 years and to cope with these new technologies?
Absolutely. You look at what I do on a daily basis, right? I have things like onboard chargers, which essentially is high power electronics, right? So I used to work in, my previous life was working on server power supplies and telecom power supplies.
Oh, blimey.
In an internal combustion engine, you don't have that charger, right? And so that whole piece of, high powered 22 kilowatt onboard charger is not present. And you have to have expertise in these OEMs or car manufacturers to do this stuff. Where, honestly, that was all in server power supplies or telecom, or even in industrial power supplies, right? Or if you look at a battery management system, obviously internal combustion engines don't have batteries in them, but all of a sudden you've got stacks of 200 cells to create an 800 volt system. And then, to your point earlier, we've got safety issues to consider, because how do I make sure that I charge those batteries within limit? I don't let them overheat, go over voltage, and how do I not let them undercharge? And I've got human life in the car that I've got to make sure that there are no severe accidents or anything. That's where the silicon really comes to play, and that's where this silicon expertise needs to reside, both in the manufacturer side, like the silicon manufacturer, as well as at the OEM. So it's a huge shift, and it's not an easy one.
It's really interesting, actually. I never really considered the situation that even though you have like a, not to name names, I say like Ford, for example, they've been around they were one of the first car makers, and yet they might struggle to produce EVs compared to someone who's got a team of electronic engineers and software developers who know how to essentially work that hardware from the ground up. Which brings me to another point, which is about software-defined vehicles. And I find it fascinating that a lot of hardware is trying to sort of become virtualized in the way so that you can essentially make updates over the air and all that kind of stuff. So what do you think, well, what would you say is, what do you anticipate from software-defined vehicles going on towards the future?
So that's an interesting topic. At CES this year, where TI had a large presence, I had the chance to walk the floor, and obviously everybody was talking about software-defined vehicles, including TI. And so if you look at the overall architecture and that is being deployed across all OEMs today, they are moving towards this type of what we call zonal type of architecture. And the idea is that instead of grouping functions by, like a body domain controller or a, window module controller, or like an onboard charger controller, like I don't have controllers based on specific functions, but I'm actually grouping them based on functions. So I maybe have like a north zone, which is taking care of like everything that's in the front part of the car. And I maybe have a rear zone, which is taking care of every function in the rear. Now, we're not there today, but the overall essential idea is to move to this zonal architecture where I then have a central compute unit. And the central compute unit basically it would have like a TCU or a basically transmission control unit that kind of has like a 5G network connection to the cloud. I can take updates in there, and then I can basically pass on updates to the zones to actually provide benefits to you as the driver, to provide kind of customization and everything. I mean, clearly one other point is I read the CEO of GM, Mary Barra. She was saying that very clearly during the COVID times, people really wanted to personalize their vehicles because that's probably the second most important vehicle or purchase in their life, right? And so, having that ability to customize, to actually make that vehicle yours, that's really all what this software-defined vehicle is all about. But I cut you off.
No, that's a really good point. And you mentioned something really interesting, and I had completely forgotten the point. But it was about zoning. Yeah. So what I find, so that's another change, isn't it, in terms of the construction of vehicles as well? Which is that if you look at a typical, internal combustion engine car, you do have like an engine controller, and which connects to all the various different points. But the car is essentially decentralized. Mostly decentralized. So you'll have some electronic system here, electronic system there, but there isn't really a central processor that kind of orchestrates the whole thing. But that's a really interesting design change or a design move, as you suggested, which is that in the future we might see a central computer that's located on the vehicle and then has control of everything around it. And of course you have your zone systems whereby you can isolate different areas and make it a bit easier to sort of handle. But the idea of a central computer essentially makes the car, it pulls the car from its extremes into a singular point. And,
yes, and
yeah. I'm sorry. Go on. Sorry.
That is, I mean, it's not of the future. That's here today. I mean, I think that we're gonna, there are vehicles on the road that are doing that, not to the extreme level, but that is very clearly where industry is headed. In a, let's say, from model years 25 onward. What I wanted to say is that this type of architecture is really no different from what we've seen in server, for example, right? This super compute type of, cluster, cloud type of stuff. It's the same kind of concept. It's just kind of a natural evolution. We talked about how auto is a little bit slower and all this stuff. It's basically, we're still walking the path of all these previous industries that have led before us. But the central compute brings us, we talked about this software defined portion, right? But as you look at the overall trend of things like autonomous driving, I'll just jump right into it. For example, it just makes sense to move to central compute, because if I have a car and I've got 360 degrees of data, right? I've got radar from the front left, front right, and rear, and maybe I've got camera data, and then I probably have some other kind of like, other type of sensing, what we call sensor fusion type of data. I don't want to have the edge nodes actually compute everything before they send everything back, right? The central compute unit, in order for it to be effective in autonomous driving, to decide when to do lane change or when to overtake, right? It needs to be able to have the data centrally so that it can then process and figure out what I want to do next. If you're processing the data for me on the front left side before I get it, I don't have a chance to actually, apply intelligence to it, right? And all the rage these days is AI, of course. And you can kind of say that that's where we're headed in automotive as well, is we want to have this data available to actually centrally compute.
And it comes back to that safety point as well, which is that if you've got various sensors that are trying to compute data for you before you even get to process it, that introduces latency issues. And I suspect if you're traveling 70 miles an hour down a dual carriageway or something, and you're going to make a lane change, you need to know immediately if there's a vehicle there, and the last thing you want is for your sensor to take 10 milliseconds to respond, because that 10 milliseconds could be the difference between having a collision and not.
And that's, yep.
Carry on, sorry.
And that's exactly what we're doing in a lot of the devices that we're coming out with. So if you look at our recently announced radar chips, we actually have basically this kind of 360 satellite type of architecture where we are doing some FFT processing of it, but we're basically sending optimized FFT data back to the central compute center via Ethernet, right? So these vehicles are actually having very advanced types of in-vehicle networks, right? So it's again very much like servers.
I've seen the rise of Ethernet across vehicles, which is a nice thing to see as well, because I suppose you get your benefits of high-speed connections. You get the fact that it's twisted pair, so obviously it's going to be immune to things like noise. And then you've also got the fact that because it's also kind of like a generic connector, it's very easy to plug and play different modules together.
Correct.
And in terms of expandability, of course, all you need is like a central network hub that you can just add more devices as you need.
You got it. And the really famous electric truck which was announced, right? That company basically was talking about how they're using Ethernet as a backbone.
Yes.
And so we have a lot of different types of interfaces available in vehicle. The most famous of which is CAN, right? That's this in-vehicle network which is used today. And there's a lot of different protocols that are out there, like CAN or LIN or FlexRay or Ethernet. And as we talk about these new vehicle architectures and software-defined vehicles, right, there is going to be basically this consolidation or a movement towards kind of like the protocol that's most efficient, that's most, that provides the most speed and provides security, as well as has some safety elements built into it. And clearly Ethernet is one of them, right?
I do wonder, and this, I might be wrong about this, but if you're using Ethernet within a vehicle, and this comes back to that functional safety issue, by having the ability to do, gigabit and beyond, does that improve its ability to be safer in the sense that if data that is sent is incorrect, it can be resent within a very small time period, or is that not really something that would happen, do you think?
So I'm not a functional safety expert, although I do have my TUVs. I do have my certification, so I should know this answer. But in general, there are different metrics that you need to meet to be able to hit different ASIL levels. The speed itself is not going to be a metric for whether you're going to be functional safe or not. I think you're going to need to basically implement various safety checks. So for example, the most obvious one might be like a CRC or a frame counter or something. So I think while the latency is one specific metric, it is only one thing which actually will be considered in the grand scheme of things. So yes, latency will matter, but you will also need to do other things like, of course. Cyclic checks or others. So yes, but in general, that's one angle which could be applied for the analysis.
Because one thing I kind of had in mind is if you had a sensor and it sent some data and it was incorrect, because the connection speed is so fast, you have that sort of window to resend the data again. It's such a small time frame, so it kind of gives you the ability to send multiple packets, and then you can kind of like and that. Whereas if you've got a much slower bus, you might send one message, it's wrong, and then you have to wait for another one, but it might take a lot longer, and so it kind of introduces that speed issue.
Right. So I'll bring up a really cool technology that we worked on is something called wireless BMS, right? And we talked about this all of last year. And again, this will depend on the actual system. So every system will have to define its safety goals, right? So maybe if I have a battery fault or if I have an overvoltage on my battery, I need to tell the driver within 5 minutes that there's going to be a thermal runaway event, right?
Yeah.
Then that basically rolls down into different requirements for when I do my battery monitoring, then I need to be able to respond to the master controller within X number of milliseconds. So yeah, this is how it would all work into the functional safety type of system level calculation. So the latency will very much depend upon what is the system requirement. So yeah, it definitely helps to be quick like that.
Interesting.
So we, in that wireless BMS system, we do implement things like I said, like these CRCs and frame counter checks and all that stuff. But we also do implement retries, right? Because in a wireless system, you're going to have basically data that doesn't correlate. You don't have something that doesn't match, and then you have to resend it. And then, so that the length of time there will definitely matter.
Now, there are some different things you wanted to share with us on the podcast today. I believe that's three different product areas you were looking at, which sort of relate into functional safety?
Yep, we sort of hit it earlier. So we have basically a new radar device that we just announced, which is ideal for what we call a satellite architecture. And then we also have some drivers for what we call high voltage disconnect. And that's kind of a really cool topic because I don't know if you've driven an electric vehicle or if you've been around one. When you turn on the car, you'll hear these clicks, right? And that's basically these high voltage connectors, contactors that are turning on.
I drive
and
a hybrid. I'm just trying to remember if I don't hear clicks. I just hear really high pitched whining.
Yeah, so it's probably well masked, but there should be these clicks that you can hear on these contactors,
Right.
and what that is essentially, you can imagine like your electronics. You have a battery, and you're kind of putting the terminals directly onto the.
It's like a big relay, I suppose, isn't it?
Yeah, right, exactly. So let's talk about the radar first, and maybe we can talk about high voltage disconnect after.
Go for it.
So we talked about these software-defined vehicles and the move towards this central computer, right? And the fact that we are moving toward this zone architecture. So one of the most important things that is happening in the industry right now is we are trying to move towards let's call it level 3 or higher autonomous driving. And as we move to that level of autonomous driving, we have to be safe. We have to be able to have the central compute system be able to collect all the data from different regions. So this chip that we came out with is called the AWR2554. You can research it online. Is basically a 77 gigahertz radar chip, which essentially is the world's first optimized radar device to be able to send data. It's optimized for what we call satellite architectures. So you're going to have radar all around the car now. And instead of processing it at the edge, which is what I mentioned, which is what was done with radar before, it actually sends FFT optimized data back to the central compute system, again, via Ethernet. So we're getting data quickly and efficiently, right, via these FFTs that are already done to the central compute so that it can make these decisions. And so this is one of the biggest trends that's happening is basically this central compute, software-defined, ultra safe, ultra fast, autonomous driving. And that's what we're essentially enabling here with AWR 2554.
Just to be clear, 77 gigahertz, that's the millimeter wave band, isn't it?
Correct.
Yeah, so,
and that allows us to, look at, so there's different types of technologies in millimeter wave. There's 77 and there's the lower frequency stuff, but, there's some which it's optimized for like long range, some is optimized for short range. And also you want to have that type of resolution just because you want to be able to differentiate between, let's call it a parking cone versus like a pedestrian on the street. So if you're doing autonomous driving, I really need to differentiate between those two. And so 77 gigahertz gives me the ability to kind of differentiate between those types of objects.
And so just to be clear, we're talking about 360-degree vision so you'll have multiple radar transducers essentially around the entire vehicle itself.
Yes. So if you imagine your car, you'll have maybe 3 radar sensors in the front, because that's typically you'll have like left, center, and front, and then you'll maybe have 2 in the back. So 5 total radar sensors gives you 360-degree coverage, and that data will start overlapping, and the central compute system is essentially trying to interpret what is where, and that's what the satellite architecture is all about, is having optimized data to let the central compute system decide what it is, instead of having you tell me what you think something is, and then maybe the right side
Exactly.
module tell me something.
So,
What
so the
something
way
is.
so the way I see it, it's kind of like a typical parking sensor. It sort of beeps when it tells you getting close to something, but that's already processed it and told you you're close to something. When what you're really saying is, I want the
Yes.
raw data from the sensor, and I will
Yes.
decide if something's there or not. And
Correct.
now you talk about optimized FTT, which I think is quite interesting. So, are you saying that these sensors do a little bit of processing just to try and simplify the data to some degree, so it's sort of faster for the main controller to work with the data?
Yes. So in our chips, we have basically an analog front end, which is basically doing all of the 4T, 4R type of transceiver receiver type of stuff, and that's just
Right.
strictly analog. But we do, see, the TI is very famous for, you might have heard of like the C2000 type of architecture, or the DSPs that we've used to do in the past, and so we have
To be fair,
leveraged this.
I can't remember the chip name, but there's one that I actually currently use, but I specifically use that for RF stuff. So that's going to be that's in the 1090 range.
CC.
So, it's close. CC something S. I am very familiar with that chip.
Like a ChipCon, like we purchased a company called ChipCon, but CC26XX or
Yeah, that
other
does
stuff,
sound. It sounds very. Yeah, it does sound a bit like
yeah.
that, actually. Yes.
Yeah, so the CC devices have an MCU that's built into them. They might have like a small ARM, but what I'm referring to is basically we have these. TI has a very long history of the C2000, what we call DSPs in the past, right? They're called MCUs now, but these digital signal processors is what they're called, and they're really good at doing FFTs. And essentially, what we have inside of the AWR 2554 is an MCU together with a DSP engine. It's a derivative. It's a specific derivative of the C2000 family, but using this, we are able to pre-process data and do the FFTs and then send back via Ethernet. So
it's a really interesting sort of like definition there, which you mentioned about microcontrollers, because to call that chip a microcontroller would be kind of I would say it's wrong, because it implies it's just a CPU, runs a bit of software. But in this case, it's actually also doing analog processing. It's also taking in that digital stuff, and then it's actually turning it, into a signal that can be used by a different microcontroller down the line. So it's got a lot more inside that chip than a typical microcontroller would have, essentially.
Yeah.
Yeah.
Right, and there's also a lot more hardware acceleration, if you will, because if you remember our school days, it's been a long time since I've done a lot of the coding stuff, but you don't want to typically use the processor resources to perform an FFT. So you've got pipeline architectures, and you've got hardware modules and stuff which are specifically designed to handle these tasks instead of using the CPU cycles to continue to crunch the data.
So next up, we've got the high voltage switch contacts, which you were talking about earlier, which are used in EVs for, I suppose, for transmitting power to and from battery packs. So could you tell us a bit about that?
Yes, there are two types of high voltage disconnection systems inside of a BMS, and you may not realize it, but it's really the same thing as what we have in any kind of electronics, right? So first of all, if you just think about a hair dryer or something that's any piece of electronic, there's going to be an on-off switch, right? Yeah. So just like a battery management system, I do not want to leave the hair dryer running all day long. Even when I'm sleeping, I want to have a disconnect, right? I might even pull the plug from it, but there's going to be a switch. And in these BMS systems, battery management, I will have essentially a relay or a high voltage contactor. And these have to be driven a certain way. And also, the other corollary is, if I look at a hair dryer, there is typically going to be like a fuse inside of the switch itself, right? So if I draw too much current, that fuse will blow, and I basically have to reset it, and or maybe just change the fuse altogether. So there are both of these elements, one of which we call as a pyro fuse, is a quick disconnect element in case of an overcurrent. And then there is kind of like these high voltage contactors, which are essentially relays or on-off switches, right? When I park the car, I want to disconnect the BMS. When I turn on the car, I want to turn it on. So let's talk about let's walk through driving of a car first. So when the car is parked, I've got an 800 volt battery, and it's literally disconnected from the inverter, right? Remember, we're talking about battery electric here, but I will be connected to, for example, the onboard charger. So the onboard charger would be connected to the wall, and so I've got AC current, which is being turned into DC, and I'm then using for example 800 or 400 volts to charge the vehicle. In that case, my contactors would be switched to kind of connect to the onboard charging port. There's a charging gun, but the minute that I get in the car, I don't want the onboard charger connected, but I need to connect the battery to, which has now been fully charged, to the traction inverter system. And so there will be another set of contactors which are designed to connect the high voltage battery to the electronics downstream. And so even when you do that, getting a little bit geeky, you can't just, because you're talking about high current and high voltage, you can't just turn on the contactors, both the plus and the minus, to just enable the car right away. There kind of needs to be a sequence to handle inrush. So there's something called a pre-charge contactor, which might actually enable. It might be a large resistor in there, which actually has a limited current to actually get the voltage up on the traction inverter side, and then I will turn on the high voltage contactors. So in an electric vehicle, I've got these contactors which I need to control to enable smooth operation of the vehicle, to enable charging paths, to enable driving, and even to enable parking where I want to disconnect the battery. Also, don't forget safety, which we've talked about quite a bit, right? If I've got the battery which is in a dangerous state, which I know it's going to fail, maybe I've got some AI in the system where it says, okay, 10 hours from now, you're probably going to have a risk event. I'm going to want to disable or open up the contactors to not let the driver drive the vehicle. Or if there's an imminent fire, I'm going to want to disconnect because I don't want the current to continue to spike and let thermal runaway happen. So the point is that in these vehicles, I have these high voltage contactors. And you can find them online. They're made by various companies. They are, as you mentioned, just high voltage relays. But they also are, they have quite a bunch of unique requirements because they are essentially coils. Well, you can buy them in two types. You can buy them as basically optimized ones, which are, they'll have like a process MCU inside, and you just have to tell it to turn on and turn off. But the smarts and all that stuff is embedded into that contactor. But more and more we're moving toward these types of non-economized types of contactors, which require, they're just simple coils now. And you have to be able to drive them efficiently. So there needs to be kind of like a peak current that you supply, and then you apply a hold current to continue to hold it open. Now, if you have too high of a voltage across them, then they're going to have like faults, like they might be welded shut, or even the system, it needs to be able to check, right? If I close the contactors, we're talking about functional safety. The system needs to be able to check to see that, have I closed the contactors for real, or have I really disconnected the contactors? So you need to basically have both an efficient method to drive these contactors, so that saves power, and then you also need to have intelligence to make sure that they're not welded shut, that they're not failing. And so that's what these contactor drivers that we've come up with, the DRV3946, is really the world's first closed loop contactor driver, which is designed to do closed loop control of these contactors. So you just need to literally tell what type of contactor it is, what's the current that needs to drive, and it will do kind of like this closed loop control because it has integrated current sensing, and it can tell when the contactor is closed and when to regulate and so on. And so when we have these optimized conditions, I have a more efficient system, right? Because remember, power electronics, right? I don't want to waste that much power. We're talking about efficiency. So I'm getting a more efficient way to drive these coils. And these contactor drivers, these DRV3946s, have the diagnostics that's built into them. So it can actually tell the system, hey, I'm about to get welded shut, or the current's too high, or the voltage on the left side and the right side is not matching. There's kind of a problem here, and it kind of helps with that overall functional safety use case. So I've said a lot. Maybe you can let me know if you understood that.
I was really interested in what you're saying, because my first question actually would be, your driver, is it, so if a contact does weld shut, is it able to detect that?
The contactor is not able to detect it. It's a dumb thing. The DRV device will be able to actually increase robustness because it has a quick discharge circuit. And this is what's really cool about our part, is that we have a discharge circuit to actually prevent the actual welding of the system. In addition, we will also signal, right? So we will also signal, hey, be careful, there's this potential welding condition. But the fact that we have this intelligence that's built into the contactor driver is kind of what's really first, right? Is that we can drive it efficiently. We also know in advance when things are going to happen.
I think it would be fair to say as well that as in the beginning of the podcast, we talked a lot about safety of these new vehicles and all the new technology coming out. And I think it is a recurring theme where you see EVs often setting on fire or failing in a very spectacular way. And so being able, like you say, being able to disconnect the power, not just reliably, but safely and intelligently, could go a long way into protecting people's vehicles. And I tell you something I've seen a lot as well, where I could see this being quite useful. Speaking of charging circuits, it's amazing and this could even happen to the best of, even the best automotive companies this could happen to. But I've seen sort of like the cheaper batteries or cheaper things like e-scooters, e-bikes, that kind of thing. They get plugged into a wall. They get plugged into a wall wart, and then they catch on fire, and the whole house burns down. And it's because of some poor design. But even then, in a high-end automotive system, it's still possible that a component could break and lead to a condition like that, where the whole car goes up in flames because the charge is not working correctly. So to have that kind of contact that can go, uh-oh, something doesn't look quite good, disconnect, and then essentially prevent that in the first place, could be a major step forward in terms of charging safely.
Yes, and a lot of those two-wheeler or e-bike type of applications that had these issues, really, again, we talk about functional safety, they actually didn't use chips which were actually designed for this type of use case.
It's almost like they've used chargers found in phones and tried to apply it to a battery that's 100 times more powerful.
And the world has realized that, yes, functional safety matters. And that's where, before I forget, that's where the other type of device, right, this pyrofuse driver, and that's another type of a method where we protect the vehicle, right, is, again, I refer to the hairdryer example, where if I draw too much current, there are various mechanisms that I have in place. And one of the mechanisms under overcurrent is I would have a melting fuse. Now, melting fuses kind of are relying on physics. So basically the fuse physically melts. But I would need a certain amount of current over a certain amount of time in order for that melting fuse to trigger. Now, if I'm talking about an electric vehicle where I'm actually talking about 800 volts and maybe a short circuit condition of, let's say, 2 kiloamps, which is significantly higher than anything that we're dealing with, right? The time that you have to disconnect is not a long time, and we cannot rely on things like melting fuses, and that's where the industry's moved to these pyrofuses. So pyrofuses, as the name implies, are these disconnect circuits. They're essentially fuses that have when it's triggered, it has an internal explosion. That's why we call it pyro, and it will actually disconnect.
Blimey.
So it's more of when our system, our BMS system, we have these chips that actually measure current and so on. When we measure an overcurrent, we immediately are able to signal to the driver to say, hey, overcurrent, blow the pyrofuse. That is where what we call these milliseconds really matter, is the driver really gives us that very rapid response to an overcurrent, is that all of our chips work together in a functionally safe manner. The overcurrent device says overcurrent, pyro device driver says, hey, I'm going to react really quickly and I have enough current to actually blow that fuse.
So just to be clear, because I've never actually heard of a pyrofuse until this podcast, so it's basically like a small detonator inside of what's essentially a piece of wire.
Yes. So you can imagine it as like a...
And I imagine is it a 4-terminal part? I imagine you've got like the current going through and then you have like a secondary sort of controller?
Correct. And it's basically I think it's like it's a 4-terminal part, right? So basically there's an input and output, and then there's like it's an internal bus bar that gets blown if there is a overcurrent. But yes. So it is essentially
Blimey.
Blowing a pyrofuse. We were playing with them in the lab, and you cannot technically fire them in the lab because it is an explosion internally.
Are they really that like spectacular when they go?
We have a video online. I think you can see it. We had these remote controlled cars that were kind of simulating like a crash. So the other condition that triggers this is like a crash, right? If you crash the vehicle, I don't want any kind of overcurrent, so I'll just pop the fuse. So we did it for, we had a video for CES last year, and you can find it online. But when that pyrofuse fires, there's kind of a piece that flies up in the air. So it's like,
oh
boom,
my
and then it just,
God.
Yeah. So it's kind of a one-time irreversible event. Right. But it's designed to be quick, right? It's
It sounds a bit frightening, actually. It sounds like you've got a hand grenade stuck in the back of the car ready to go off at a moment's notice. But I suppose, like you say, if milliseconds matter, that detonation is going to be the difference between a battery potentially exploding when it hits the car, or leaking fluid and not doing too much. Well, I suppose leaking fluid depends on the battery technology, but the difference between them having a serious meltdown or not. And so you need to be able to drive that quickly. But my question is, if pyro fuses already exist, then what is it that the driver itself is doing? Is it doing that intelligent thing where it can basically read the car and see there's an issue and then trigger the fuse itself, instead of relying on some kind of custom solution to do that?
Yes, correct. So the pyro fuses, first of all, are not in every single car. These are kind of newer elements that, as we move to 800-volt vehicles, right, there's a need to disconnect quickly to prevent kind of dangers. But yes, the pyro fuses all follow what we call an AKLV standard for triggering. So there basically is a current profile that needs to be followed, and all these pyro fuses which are on market, TI doesn't sell them. We only make the driver, but once you follow that, they'll blow. But again, we have to do diagnostics on these pyro fuses. So to check whether the supply is up, or to check whether the normal ohmic condition of the pyro fuse, right? We have to continually check and say, hey man, the system, the pyro fuse is operating as expected. The pyro fuse is operating as expected. Oh, I've detected that there's an anomaly here. Let's go alert the system, right? Because we're talking about safety. So there needs to be continuous diagnostics and checks on the power supplies, on the status of the pyro fuses, the ohmic conditions and so on. And so that's what these things do, is they have that intelligence, again, that's built into them. And we're able to not only fire within milliseconds, but also report any kind of risk that's available.
But how can you report if you've just cut the power? Obviously, you'd have a secondary bus of some kind with its own sort of power supply.
I think the system would also have, I mean, just thinking about it, I'm not a car designer, but I think they would also have like a challenge response type of thing, where if there's no response back from the pyro, then you assume that something's wrong and you enter a safe state somewhere. So, again, we're talking a lot about functional safety, which is great, because I think this just shows the in-depth detail that you have to get into. But, every state of the vehicle has to be defined, and you have to define basically a safe state that you want to enter if this event happens, and so on.
Fantastic. So we've looked at the radar, we've looked at the high voltage switch contact drivers, and then we looked at the pyro fuse drivers. Now, going forward in the next sort of 5-10 years, what other drivers do you expect that you'd like to see in new EVs?
That's a really big question. I cover a lot of different segments. I'll maybe talk about some of the things that I think will happen. I think EVs are headed towards what we call this software-defined vehicle route. I think the intelligence that we have, the silicon is getting stronger. We're getting better. We're getting cheaper. You have the ability now to have a supercomputer on a car, and I think that eventually it's not going to be too long, but before we have data that's managed and pumped into the cloud. So whereas all of our phones and our personal lives are connected to the cloud already, the vehicle is really the one last thing which isn't connected.
I think you're absolutely right.
And so things
I think you're absolutely right.
Right. So things like doing things like fleet management, or for a corporate operator, maybe if you're a rental car company, to have data statistics on how your cars are performing over time. To have if you're an OEM, to know how your vehicles from model year 25 performed in its lifetime in different regions of the world and different humidity levels and so on. And, why did this person crash? It's kind of that big data. And it goes along with this whole AI crunch, is that we're going to have tons of data that's going to be available for us with these connected cars now. Even for us as drivers, the benefit is really going to be in terms of driving range, because now we're really going to be at the limit in terms of what does material science give us? What type of batteries can we do? How accurately can I monitor them? Well, the next phase is really going to be, how do I leverage big data to optimize driving distance, right? So I know that Robin, has a lead foot and he drives like crazy, and I know Mark basically drives much easier. And
you're not wrong there. I'll be honest, you're not wrong there. To be fair. But I think I think what is really fascinating is how, like, because you've said again something I really resonate with, which is that the vehicle is the last sort of thing that we use every day, and it's still not essentially electrified. It's still not in the cloud. It's not like your mobile phones or your computers. It's still almost archaic, and it's funny to think how that probably comes down to, obviously safety is a big factor because we can't just throw any new technology into a car without fully testing it first. But the fact that because most vehicles on the road right now are internal combustion engines, and because they're fundamentally based on fossil fuels, some liquid fuel being burned, it's not really a high priority to get electrical systems in and out of that and like software. So it's really interesting to see how it's taken for the introduction of batteries and EVs to finally make those vehicles, intelligent in the same way that maybe our laptops or our smartphones are.
Yeah.
And so what? And I think this comes down to another area which I do foresee, which I personally don't, but I can see how this the software-defined era is going to be software features where you need to seat in your car, pay for that as a, which is something I can understand done.
That's an interesting as well, because I am a veteran in this industry now, and as I look at my daughter and what they're used to, they're just very used to paying for different types of features to be enabled and all that stuff. And I think there's going to be a point like where we see today where there's exhaustion in terms of paying, doing these pay for models. But I think personalization is really, as I talked about, it's really the name of the game, right? If you want that last extension of yourself, which is the car, to be connected and to, look at your phones, we all do cases and do different wallpapers and stuff. I think that is where the industry is headed.
And that kind of reminds me of the only personalization I've ever seen in a car is where they have the two buttons, one and two, where you can push it and it changes the seat slightly to the position that you have, and then that's the only personalization you get. Everything else you've got to reconfigure from scratch. But like you say, if you had a software-defined system, you had your phone with you, you could put your phone down on the dash, it recognizes who you are, the fans change, the environmental controls change, the screen changes, the seats change, the windows change, everything sort of configures to your setup, and then you don't have to sort of mess things around. So I suppose before we wrap up this podcast, is there anything else you'd like to talk about with our audience?
I think in general, I think what you'll see is that Texas Instruments takes the overall shift in vehicular architectures, this overall software-defined vehicle, this overall functional safety, and trying to maximize driving range and all this electrification. We are taking that to the next level, and what you will see over the next months, next years, is just a continual announcement of new devices that we will introduce to the market, whether it be for battery management or onboard chargers or thermal management or traction inverters or central computer systems, radars, any types of like current sensing or any type of like general analog sensing. TI is really pushing the pedal in terms of helping our customers design next generation vehicles.
And just before I wrap up the podcast, finally, if there are engineers out there who want to get their hands on these products to test them out and integrate them into their solutions, what would you do and what would you recommend?
They can get it through ti.com. So www.ti.com, go to the product folders. So the devices that we mentioned today were the AWR 2554, the DRV 3946, as well as the DRV 3901. So the easiest way to do it, I basically go on to ti.com, search for the part, and you can get into the product folder. Now, some of these products are behind kind of a security firewall because they're functionally safe products. We don't want everybody using them in not approved ways, or we want to be careful that people understand how to use it. And so you do need to get in touch with your TI representative to get full access to the data sheets. But overall data sheets, overall specs, you can find them on ti.com as they've been announced.
Fantastic. Well, thank you ever so much for taking the time to talk to us today.
No problem. Thank you.